In this question, we're going to talk about where does this not actually work in practice? Where does all of this analysis blow up in our faces and not actually help us do any sort of analysis that can apply to the code that we need to write, the code that we need to make fast? Let's take a look. Historically, some things are just slow in Python. The intuition you might get by looking at big O and looking at the different data structures that might be derived from or motivated by this big O analysis is that, oh yeah, I'll write a prefix tree. Oh yeah, I'll write a skip list or a Bloom filter or something like that. But in truth, the implementation of some of these things at the pure Python level may not actually be better than what you can write using the built-in types. Built-in types are heavily optimized. Things like the sort method and the sorted built-in function aren't a merge sort or a quick sort or a bubble sort or a selection sort, but a heavily optimized hybrid sort that combines the fastest of all the different sorts based off of anticipations of what the input data would look like and what the original size is. Because of course, when you think about it, operationally, sorts which require that you copy data are going to be slow because it's slow to allocate memory. Sorts which work on non-contiguous data are going to be slow because pointer chasing is slow. Python objects are very large, so creating your own Python objects that represent these data types might actually be very inefficient because you're having to deal with the enormity of the weight of an individual element in Python. But I want to show you a narrow example for where this might not actually play out as you expect in practice. And I want to revisit our binary search. Here is our simple binary search. And you can see we implemented this as a recursive algorithm, a divide and conquer algorithm, and theoretically this should be log n performance. Theoretically should be better than our linear search. Let's actually time this. Let us time a naive linear search against this binary search. And let's see how they behave in practice. And the news is not really that great. The binary search is worse on much smaller structures. It takes up to about 1,000 elements before it pulls ahead because we anticipate from that big O analysis, it will eventually pull ahead. But when it pulls ahead, it's actually worse on the really big structure here, and it's actually worse on the big structure here. The linear search is actually faster because the data, there's probably fewer copies, because Python function calls are very slow, or at least historically they've been, because every time I implement this search, I'm creating this kind of view which might result in an allocation. There's all sorts of details for which this might actually, even up to large sizes, not be better than what I can do with the naive approaches. One of the reasons why this might be slow is because we do see historically a penalty for function calls in Python. And this is why we have this restricted computation domain approach in Python. This is why whenever we're dealing with NumPy and darray, we always try to keep within that restricted computation domain. We try and call these large level aggregate functions that immediately drop down into C and then do everything at the C layer on contiguous memory without dynamic dispatch. Well, if you think about it, for a structure of size 100,000, if this were actually doing an even divide and conquer, there's only going to be 11 steps. There's only going to be maybe 11 or 12 Python function calls. And so the question is a Python function call so slow that calling a Python function 12 times, divide and conquer style, is going to be worse than doing a linear scan on a very large structure? And that may be what we're discovering in the previous case. But I want to narrow our view a little bit tighter than that. Because one thing that we might also know is, as a consequence of the formulation of this problem, the recursive formulation of this problem, we're actually limited by what we can do with it. We know that if we try to recurse in Python greater than a certain number of times, we hit this recursion error. And so, yes, it is the case that for a divide and conquer algorithm that partitions its data set into two halves, it's probably the case that this should be log base 2. So here we'll do log of 2 here. It'll only recurse maybe 16 times or something like that, but still, there may be circumstances under which, in pathological cases, this thing blows up in our face because even though it's supposed to recurse only twice, the partitioning wasn't even, and we hit some bad case where everything just where we partition only tore off one item. We see things like this for example, there's one of these corner cases for things like regular expressions. We might be tempted to do things like get or set the recursion limit. And you might have even seen somebody do something like this, like a context manager that gets the recursion limit, doubles it, and then sets it back. Don't do this. Don't ever do this. This is even worse than the context manager that I saw somebody write the other day, where they said context manager, retry, and they retried a function some number of times. Actually, it was a decorator, where they were like, oh, here, I'm going to write a decorator that retries a function. Do not do this. This is going to cause so much pain in your life. Something like this. For in range 3, try to call the function and return the value. Otherwise, just kind of keep going. And then here you raise some error. Don't do this. Don't set the recursion limit, because obviously what you can think is the operational mechanics of how this code works, what that recursion limit should be set to, how the interpreter works, is almost never going to be scoped narrowly to an individual function. So if you try and set the recursion limit at this level, this is going to cause some conflict with somebody else who expects the recursion limit to be something else, or expects certain behavior, or maybe even expects the recursion limit to stop them from recursing at some point. Similarly, in this case, what do you do upon failure? Just skip it. It's almost always the case that what you do upon failure is ad hoc to the code that you're writing. How you execute that code and what the recursion limit is almost always going to be ad hoc to the code that you write. So these things are just very bad ideas. And in general, if you're recursing so many times that you hit the recursion limit, you're probably already doing something you shouldn't be doing in the first place. Because we know from simple examples, like the Fibonacci example, the canonical example of the implementation of a recursive function, there's much better ways to write our code. Instead of writing Fibonacci like this, fib of n minus 1 plus fib of n minus 2, which definitely blows up with that recursion limit. Here's our base case. If n equals 1, return 1. Here's our 2 base cases. Instead of writing it like this, which will 100% blow up with us, by the way, this is a base case, and this is our inductive step, or iterative step. Instead of writing like this, we can write it better. We can write this as a generator, right? So we have better formulations for writing our code that avoid these problems in the first place. Don't try and patch over them. It's just going to end in tears. Now, I want to show you one very interesting consequence that we can see. Here's a very simple recursive function. And here is one of the things where if we were to implement some code as a recursive function, it may be the case that this big O analysis may not actually give us real-world operational guidance, in part because the pain of recursing in Python, the pain of calling functions in Python. So our goal might be, how do we perform transformations of this? And we can dip back into our computer science courses to realize that recursion and iteration are both really only implementation characteristics. They're really just about whether you internalize or externalize a stack. They don't actually exist in the same way that some of these other things do. The machine doesn't really distinguish between those. It's really a human concept for how you model the function, how you write the code, not really how the code is executed. Well, here's a very simple recursive function that just counts up to 10. And I want to show you that we can do things like take a look at each one of the steps in this. You can see each of the number of frames that we have, and you can see how this thing is recursing. You can see the local variables for each iteration of this. So you can see n goes all the way down to 0, then it recurses back up. And when you look at this, you can see in Python, we are maintaining a dictionary for each frame, which corresponds to each invocation of this function, which corresponds to the number of times we recurse. The recursive formulation is about using the implicit frames for the functions and the implicit stack-like nature of calling a function and returning from a function for data storage. There is necessarily always a transformation from a recursive formulation to an iterative formulation by taking that stack and instead of making it implicit in the interpreter, making it explicit in the logic. And I want to show you how you can do that. In fact, it turns out it's very easy to do a trivial transformation of this. All we have to do is introduce the chain map and the collections.deque. Here we are modeling our scope not as a bunch of function frames that are connected to each other in some sort of stack where invocation adds something to the function frame and return pop something else, but instead we're implementing this as a chain map where we have a deque and we pop and append to the left-hand side. So every time we recurse in the original, we just append left to our scopes. Every time we recurse back up in the original, we just pop left from our scopes. Here is an implementation of the exact same function with no actual function calls except the original function call, where all of this recursion is just being mimicked by an explicit data structure in the code itself, this chain map with the deck. And really the chain map is only there to make our lives a little bit easier. It's really the deck here. That's the interesting thing. The deck here serving the goal of having a double-ended queue, an actual stack. And through this recoding approach, we can actually deliberately take any recursive implementation and make it an iterative implementation. I want to show you how we might do that. Here is our recursive implementation of our binary search, which we know is not actually that much better than our naive, don't even bother writing anything, just use in linear search. Well, I can re-implement it by taking the invocation side of the recursion and the return side of the invocation and writing those as two for loops. On the invocation side, I just append to my scopes. On the return side, I just pop from my scopes. In the middle, I just decide what I'm going to append. So either I append the return value of false or I append the return value of true, or I just update my local scope with whatever the haystack has changed into, with whatever the needle has changed into, whatever the local variables have changed to. And really all I'm doing is I'm doing the exact same thing that the Python interpreter is doing, except I'm doing it explicitly with a collections.deque and a collections.chainmap. And I can take this implementation and I can time it and I can see, was it the case that the iterative versus the recursive is where I'm seeing this unfortunate consequence that it's not actually any better than my naive approach. And if we take a look at the performance timing, we can see that it's probably not the case that the iterative approach is the problem, because we can see that it's still just about as bad. So there's more to this. A lot of this big O thinking doesn't always work out in practice because there's a lot of things that you have to consider. Where the big O thinking works out in practice is as a risk management tool. If the code happens to be this fast and it happens to grow in this rough fashion, how does that allow me to manage my risk for needing to refactor or need to revisit it? Because the recursive versus iterative is definitely an operational characteristic, but you can see here it really didn't have a humongous impact. Yeah, it made things a little bit better, but didn't have a humongous impact. However, where these transformations, these formulations are useful is that once you start thinking in terms of these transformations and these formulations, you may find that the initial transformation is almost always a little bit more heavyweight than what you want the final transformation to look like. And so, again, we can start with our iterative formulation, and we can discover that this transformation is a very, very rough transformation. We can discover a lot more about computer science by thinking about how we can slim this down. For example, this function was tail recursive, meaning that we never really reused any details that we stored previously. We only ever moved forward. We never really moved back, like would be the example in the Fibonacci. And as we look at this, we can see places where we can start to make our lives easier. Like we don't actually need a chain map here. We really just need a local variable for the needle and the haystack. And guess we don't need that. And so here, and we don't need the scoping at all. We just need a local variable because we never reuse any of that data. We never revisit that. So what we could do, we just eliminate all of that. And I guess here, what that means we could do is we eliminate all of that as well. And so here is our second transformation, and I wonder if that transformation is any faster. And it turns out if we measure it, probably it's not going to be that much faster. It turns out that things like memory allocation is a dominating characteristic of how fast or how slow our code is, and it's one thing that we often have very poor insight into in Python. Where things are located in memory, whether things are contiguous, how big things are, we have very little control. And so when we're following this approach, it's very common that the restricted computation domain idea will pop up. We'll want to follow these approaches of finding the algorithmically best approach at the narrowest level, at the C level that we've dropped down to, because at the Python level, it may not make a difference. Because if we take this code and we time it, it's actually not going to be that much better than what we saw before. This doesn't actually make our code faster. In order to really make our code faster, we have to take this transformation one step further. And by the way, let me show you what that means one step further. For example, we could do something like this. We could take those 4 lines and make those 1 line. Because we all know that writing code in 3 lines is always slower than writing code in 1 line, irrespective of what the code does. Of course, that's not the case. Just rewriting something into 1 line will have almost no performance impact. But what we can think about, and what we do have to moderate our knowledge of Big O against, is where the operational characteristics of this code is going to be slow. And probably what the problem is, it's the slicing, and it's the data sets that the slicing are creating, the copies that the slicing is creating, and the allocations that are created there. So following our transformative approach, maybe we can identify that we don't actually have to slice, or at least we can just reconstruct this data from just a pairing of indices. And if we do that, if we further refactor this thing, and we further the refactor thing to eliminate the memory allocation portion, then finally we'll see the result that we anticipate and the result that we want, namely that the final version of the search iterative is dramatically faster than the search recursive and also grows better. The Big O knowledge is useful, it's beneficial, it's analytically useful from a risk management perspective, but it's not enough to make your code fast. But it is a starting point for tying together everything that you learned or maybe didn't learn about computer science in order to make your code better, to make your code faster, to make your code more efficient.